friends, and today's topic is basically it's completely new. We are going to prove a periodicity property. Periodicity means what? If a function repeats itself, if a function repeats itself after a particular interval of time, that function or that signal is said to be a periodic. Now, if we want to calculate a Laplace transform of single time limited or bounded signal, then it is possible. But if it is unbounded, that is, if we want to calculate a Laplace transform of a continuous pulses, if we want to calculate a Laplace transform of cos signal which is continuous till infinity, then it is quite difficult. So this periodicity or periodicity property helps us to determine the Laplace transform of periodic signal. So let's see what is said. Statement. First of all, the statement of periodicity property is if x of t is a periodic signal, then you can write this x of t as a x of t plus nt. This t stands for the amount of period which is added in x of t, so that after this interval or at this interval function will repeat itself again and again till n times, or you can take this n value as an infinity also. Now, so the Laplace transform of this such type of periodic signal is 1 upon 1 minus e to the power minus s into t, where this capital T is nothing but the period of that signal into x1 of s. I'll tell you what is x1 of s but later on, but just remember the Laplace transform of this periodic function is represented by 1 upon 1 minus e to the power minus s into capital T, which is in the power of exponential term, into x1 of s. x1 of s is much more important because we can easily calculate this time period t, but this x1 of s is important. Now, so let's see, we're going to prove this property. So, by the definition of Laplace transform, what we can say, the Laplace transform of any continuous time signal is represented by x of s, and it is integrated over the range from minus infinity to infinity, x of t, which is input, multiplied with e to the power minus st with respect to dt. Now here the input term is a periodic term, x of t plus nt. So that x of t plus nt will be multiplied by e to the power minus st dt and integrated over the range from 0 to infinity. Now, why I have written 0 to infinity? Because I want to calculate only a single-sided Laplace transform, or you can say that the function is periodic only in one direction, that is in positive direction. If I place here from minus infinity to 0, then the graph starts from 0 but moving towards a minus infinity, that is left hand side. So right now my function is moving towards the right hand side and start from 0. So let's draw one diagram so that you can understand how I am going to solve the periodicity property and what will be the actual value of x1 of s. So let's see. Now here, this is the complete cycle having time period t. Now next time period is again have t, so the total time period will be 2t. Now next one is, if we complete one more cycle, then the time period will be 3t and so on. Now what I am going to do, as look at here, this is the sine wave, or you can say it is an oscillation of an oscillator which produces a sine wave. Now just look at the first period. First period means only this period. Over here you can say that you have only one sine wave. Now if we add a delay, that is t, in this sine wave is a sine omega t. If we add a delay in this function, then it will become sine omega t plus t. This will be the delay added into a t. Now what will happen? If we add a delay, then your function repeat itself. Again if we add a delay of 2t, that is one more delay. Or you can say the total delay is now 2t. Then this sine function can be represented sine omega t plus 2t. So what you can say that your original signal is sine omega t, but after adding a delay, then it will become sine omega t plus t. If we add one more delay, then delay is now twice. So this will be t plus 2t. So you can say that only one function is there which is going to be delayed. Let's say the x1 of t is my sine omega t. If we add a delay in x1 of t, then of course the sine omega t will be also create or produces the same value but after t. So I can write here sine x1 of t plus t is now omega t plus t. So this is nothing but this oscillation is nothing but the addition of x1 of t plus x1 of t plus t. Similarly, if we add one more delay which is 2t, then the sine function is now omega t plus 2t. So I can say that this whole oscillation is the combination of x1 of t, x1 of t plus t, x1 of t plus 2t, and x1 of t plus 3t, and so on. So if we add all these value at a time, then you can have this whole oscillatory behavior of wave. So from this whole calculation, I can say that if we add a delay in this wave, then this wave repeat itself again and again. So instead of solving whole graph, we'll take only one part of this graph, which is this. We will solve only first time period, and that first time period is nothing but my x1 of t, because this x1 of t repeats after each and every values of t. So that's why in formula we have written x1 of s. x1 of s is nothing but the Laplace transform of x1 of t. Now this is all about the periodicity. Now we will solve the property of periodicity. Now how this property is going to be solved, let's see. Now as I told you, basically x1 of t is the main function and it is started from 0 to t. The time period of this x1 of t is 0 to t. But if we add a delay in t, then all the t replaced by t plus t. Now the time period is also varied from t to 2t. Similarly, in third case also, the time period will vary from, or integration limit will vary from 2t to 3t. This 3t is the final limit of x2 of 2t. And the time period is also increased. And so on till the last limit. Let's say the last limit is p, which is the time period. So upper limit, look at here, the lower limit is even and upper limit is odd. So you can say that if we want to write even value, then I will simply write pt, but for odd I'm going to write p plus 1 into t, and all the limits value will carry now pt and pt. Now just look at here the values of p is increasing. Like initially here we have p value is 0, so t minus pt becomes only a t. Now here p value is 1, here p value is 2, here and next value will be 3. So I can say that basically I'm adding the values of p from 0 to infinity. So let's do one thing, we'll equate all the values and represent or remark it by summation. So summation value which totally depends on value of p, and that varies from 0 to infinity, because here the p value starts from 0 and continues till infinity. So that's why I have substituted summation value from p to infinity. Now the summation integration value is pt to p plus 1 into t, x1 of t, t minus pt, and e to the power minus s into bracket t plus et. Now what I'm going to do, I'm going to split this power. So let's see the next part of this derivation. If I'll split the power of exponential term, then what you will get? The minus sign will come inside e to the power minus st, and next term will be e to the power minus p into st. Now the whole integration is depends on t, whereas the summation is total depends on value of p. So I will take this summation value inside and I will apply it on e to the power minus st into pt, because in whole term, only this exponential term carries or having a value of p. That's why the summation value will count only e to the power minus st into p. Now, I'll assume this p is nothing but the power of e to the power minus s into t. Look at here, I have mentioned. I'll consider this p is nothing but the power of e to the power minus s into t, because we know that power into power is nothing but the product of powers. So, there is one formula for this term. That formula is e to the power summation value start from p equal to 0 to infinity. E to the power minus st into p is nothing but 1 upon 1 minus e to the power minus s into t, where this t is the time period of first function x1 of t. The time period of x1 of t. Now, I am going to substitute this value over here. Now, as I told you, 1 upon 1 minus e to the power minus st is the common part of is a constant part, and which is a common, because the whole integration depends on t, where this whole term is independent of t. This t is not there in this bracket, so I can take this part as a common part. Now, so what else is remaining in integration? Integration 0 to t x1 of t e to the power minus st into dt. And this is nothing but the definition of Laplace transform. So what is it? Definition of Laplace transform. The definition of Laplace transform is a Laplace transform of any time signal x of t is represented by x of s, and it is integrated over 0 to infinity or 0 to given time period t, that function into e to the power minus st dt. And that's why I have replaced this whole integration part by x1 of s. And this is how we are going to prove the periodicity property of Laplace transform. But look at here, this x1 of s is the much more important part. x1 of s is the first time period of given function. After that, that function repeats itself. So no need to calculate that value, because that value is repeating after each and every value of delay. That delay is t. So we are going to calculate only the time period of first graph or first cycle, and we'll solve only that first cycle. That first cycle is represented by x1 of t, and you have to calculate the Laplace transform of that x1 of t, and you need to measure only the time period of first cycle, which is placed over here. That's it. This is how we are going to prove the Laplace transform, or you can directly solve the numericals related to that. So thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda for further more videos. Thank you so much.